So let's focus on the lesson, and we can discuss that later. So we are going to talk about the end part of yesterday's conversation, and then transition into today's. Yesterday's conversation was on the definition of potential energy in an electric field. We both discussed a uniform electric field situation in which that's created by a metal plate being positive or a metal plate underneath being negative, or more than likely the combination therein. So there's a uniform electric field. We discussed that for a charge moving in this particular field, that you have two options. So I'm just going to have this charge go this way on how you define potential energy. The first definition is in which case this is zero, and distance is defined as here's distance initial, here's distance final. Really, it's not distance. It's actually kind of like we said before at the beginning, position. And there is the change in that. And if you do that, then potential energy is defined as positive QED, with the fact that this distance is getting less. So if I want to find the change in potential energy, it's QE delta D. Or actually, let's do this differently. Change in anything is final minus initial, which would be QED final minus QED initial, or in other words, QE delta D when I factor out the Q and E. That is the first way that you can define it, okay? The icky thing about doing it this way is, as we see here to here, that delta D in this case is negative, which is true because what do we expect work to do when it goes the way it's supposed to? Positive. I know I'm repeating myself. It's for the sake of the video. I apologize. Okay, and delta U in this case is going to be negative because, as we discussed the other day, work is equal to the opposite of delta U. Okay, so that's the first way that you can define it. The other way to define it, okay, is this. Instead of saying distance initial is from this is zero, now we define the positive plate is zero, in which case this would be distance initial, and this would be distance final. And you'll notice that delta D in both cases is identical. Okay, well, in magnitude anyway. But it's negative over here in order to bring negative to this term, as we would naturally expect, because that would be negative right there. Whereas in this case, the change in D is increasing, or it's positive. Because that's the case, if you want zero to be measured there, then potential energy has a negative out in front to counteract that, or delta U equals negative QE delta D, so that when the positive charge moves the way it's naturally supposed to, delta U is negative like it should be. I am going to use this left side right over here. This is what the book also uses. Okay, as I mentioned, the pink side right over there I used for so long. And the reason I like the pink side is it's extraordinarily similar to your setup from Gravity. All right. Then we discussed in a non-uniform field, right? I'm going to try to do it correctly for the beginning today. Okay, two like charges. And I say like charges because, of course, would it matter if these were both negative? Matter of fact, we did positive yesterday, so we'll do negative today. Where are they going to have the highest potential energy? Closest to high potential energy, and lowest is going to be furthest away. And if you struggle with this, think of just an object being pushed down a hill. Where is it going to have the most potential energy? Up on the hill, where it can do the most possible or potential work. When it's far away, it doesn't. It's down at the bottom of the hill. Now, if you use the hill, actually, I'm getting away from myself. I'll do that in just a second. Where is the most work going to be done? Oh, nope. The most work going to be done, because work is defined as force times displacement. So if this negative guy right here goes 1 meter here versus going 1 meter out there, where is the most work going to be done? Closest to, because greatest amount of force. Now, I'm switching the conversation entirely, so these are not on the same setup. Let's go ahead in different colors here. Now they are unlike charges. Where are they going to have the most potential energy? Where is the hill going to be the greatest? Far away. and the lowest is going to be when they're close to. Okay? And where's the most work going to be done?
Close to.
Yeah, in both cases up here, most work is done close. And the equation becomes this. Potential energy equals KQQ over R. Extraordinarily similar to the potential energy, to the force equation. What's the only major difference? The R isn't squared, and the other really major difference, the fact that that value right there is in fact scalar. It is scalar. Yes?
So I guess this wouldn't matter if it's in an electric field, but like the attraction between the positive and the negative, once the negative gets so far away from the, like you said, the highest potential is where it's like the farthest away, but once you get so far away, the force is just going to get weak because they're not by each other.
100%, you're absolutely right. So one thing that's very helpful is the graphs that I made yesterday, and I'm going to address that particular fact on the graphs with another comment here in just a second, so I'll come right back to you. But basically, this graph, this type is constant in the situation, and so as I mentioned before, this is kind of the same thing as KQQ times the equation 1 over R. So if you look at this graph, the potential energy versus R, this is a 1 over x function when both of these are positive or when both of these are negative. So one really valuable thing about this graph is that while it is not a hill, you can very much look at it as though it were a hill. Like, where is a ball going to roll fastest down that hill? Right up here, right? Where it's very close to, right? And as it gets further and further away, do you expect its height to change very much on that hill? Even if it's changing a little bit, it's not changing very much. It's kind of like, why is it completely safe? Do I have a ridiculous amount of potential energy if I'm walking across the top of a mountain? Yes.
Yeah.
Why am I safe even though I have a ridiculous amount of potential energy?
Because things ground and
You're right there.
you're not going to jump off the mountain.
So it's not potential energy that's dangerous, it's the change in potential energy that's dangerous. Yes? Meaning, to that idea, if I'm standing on top of a mountain at, let's say, 20,000 joules of energy that would easily destroy me, and I stay at the exact same height, what is my final potential energy? 20,000. So what's my change in potential energy? 0. Now, where mountains become dangerous is when I quickly change that potential energy, like falling off the side of a mountain, because all of that potential energy becomes what? Kinetic energy. Now we have a particular issue. So, as you look at this, if I compare these two spots right here, okay, does one definitely have more potential energy than the other? Yeah, but this is like the world's most gradual hill of all time. Is there that much of a difference in potential energy between these two spots? No. And, like we said yesterday, what if one of these is negative? Well, if one of these is negative, it's like a negative 1 over x function, which gives us this right here. And now I can finally address the comment that you said just a second ago, Rihanna. Why don't we have to worry? Why do they have the... Does this spot definitely have more potential energy than this spot right over here? 100% it does. But do we expect a ridiculous change in energy between those two spots? No, for the exact reason that you said at the start of this. The force is ridiculously small. So do we expect much of a change in potential energy? No, we don't expect much of a change in kinetic energy either. That being said, if they were allowed to just go forever, eventually it's going to start going here and going more and more and more rapid, falling down the hill, aka where is it going to do the most work? Closest to. How are we doing?
Yeah, so
Okay.
it would have, like there would be a force, but it would take a long time.
And that is assuming that it is the only force in the universe and nothing else is affecting it. Ultimately, if we got, for example, let's talk about gravity for a second on Earth. Okay, This is a quick aside, and then I promise to address your question, Jaden. Last year I told you that the force of gravity is big G mass 1 mass 2 over r squared. Yes? Okay? The actual way to calculate potential energy for a non-uniform gravitational field will look extraordinarily similar to you. The potential energy of gravity is big G mass 1 mass 2 over r, with one major difference. There is a negative in this case. Okay? AKA, for gravity, it looks like that exact same side that we talked about a minute ago. Why? What's similar between gravity and this guy right here? Why does the bottom part look the same as gravity?
Because the farther you get away, there's not going to be a force in a long time.
That is true. It's not quite what I was going for right now. What is the same about gravity and this guy right down here? How do you get this bottom one? If what's negative? One of the charges. So the charges are what?
Attraction.
Attraction is the answer. Gravity causes attraction, as does a positive and negative in this particular case, which is why they look identical. Now, the reason I brought up this particular fact is at a particular distance from Earth, okay, like Jupiter, for example, is there a force of gravity from Earth on Jupiter?
Yes.
Yes. Is it significant enough that we would see any sort of impact whatsoever? No. AKA, very quickly you can see in this that it would basically, for all intensive purposes, completely level out. And would we expect there to be any change at all? Absolutely not. So while I say, and you can see on this graph, that where is the potential energy zero? Well, potential energy is zero at infinity. At r equals infinity. Really, r doesn't have to, practical purposes, be infinity. It just has to be pretty darn far away such that this is not changing very much at all. Jaden, you're next.
Is that graph work for like charges and unlike charges, or
The top part is like charges. The bottom part is unlike charges. But you mean if they're all combined together?
Yeah.
Let me address that in just a second. Yes, it does. 100% it does. Yes.
Is there an absolute zero for potential energy, the lowest it can be?
Well, no, because ultimately you got to remember that potential energy zero is a scale set by who?
I just didn't know because this said temperature too, but that's just because we didn't know we could have real zero.
Right. So what would it mean if potential energy is zero?
It means no work could be done.
No work could be done. You are ascribing essentially a similar concept to what we talked in thermodynamics of the heat death of the universe. That the heat death of the universe is that so much heat is all spread out everywhere. The molecules, every single molecule, is so far spread from each other that do they have an impact on each other? Yes. Is it significant enough to be able to cause work? No. In which case, of course, then there would not be work done in that case, so all matter in the universe would be a potential energy of zero, and thus nothing could change or be done whatsoever. Now, I'm pretty sure that's going to be really far away, and I don't think we'll live to see it. I don't even think humanity will honestly live to see it, but we'll find out. Who knows? All right. Actually, we won't find out. Okay. Ignorance is bliss. Now, to Jaden's question and leading me into the new stuff today. Let's say we have charges like this. I have a positive charge, and a negative charge right up here. Okay, we'll say that the positive charge, let's make some value.
137 nanocoulomb.
Done. Okay, put the other ones on a similar. We'll have it nano, similar value. Don't change them too much. What do you want this positive guy over here to be?
67.
Cool. Very good. And then what about this guy right up here?
203.
So negative 200 nanocoulombs. All right. So there are two ways to approach potential energy in this particular setup. Okay. The first way to put it is you can ask about the potential energy. I guess arguably sort of three. You could be asked about the potential energy of a particular charge. So I could say, what's the potential energy of Q1? Okay. The potential energy of Q1 for just these two would simply be the energy of 1, 2, or K times 137 oh, sorry, I'm going to need to give some value for distance. Let's make this an equilateral triangle to make my life as easy as possible. Okay, because that's what's really important. Okay, and we'll say there's, I don't know, 6 centimeters between all of them. So I would say U12 is K times 137 times 67 nanocoulombs all over a distance of 0.06 meters. That's the potential energy caused by this setup right here. But I would also need the potential energy 1, 3, because I'm asking for the potential energy of charge 1. So that would be K times 137 nanocoulombs times negative 200 nanocoulombs all over 0.06 meters. And the nice thing about this is energy is scalar. So guess how I get the total potential energy of 1? Add the two of them together. So do that real quick and tell me what the answer is. It is, yes. Yeah, negative 200 right there. No problem. It's questioning your decision to put it in.
I know.
Are you sure?
Oh my god, then I just put a negative instead of a, or I put a minus instead of a negative.
You guys got an answer yet? Well, it's not that hard. Okay.
We might not got
What's that? Yeah, add. What do you got? What's the total?
-2.7.
Negative what? You said negative what? 2.7
Yes.
times 10 to the negative 15th. Okay, so what I would suggest you do in this case would be negative 2.7. What's negative 15? I know negative 12 is pico. Is that?
Yeah.
Where's 15? Oh, 15 pico? Nano, pico, femto. It's femto. Relax. All right, so this would be negative 2.7 femtojoules. What'd you get?
I got to the negative third.
Yeah, I got to the negative 3 too.
Can you confirm with a few people?
Yeah.
They're not. They're slightly different. That's like saying, you know, $1 is basically the same as $1 trillion. If that is the case, new cost for my protractors. New cost. My protractors no longer cost $1. I would like $1 trillion. What's good? All right. So what are you getting? So this is negative 9. That's negative 9. Positive 9 would cancel it. So that should be negative 9 divided by to the negative 6 plus both of those. Yeah, it should be closer to negative 30.
Yeah.
So this would be millijoules.
Wait,
All right. So what does that mean? Well, let me ask you the question here. If I say that this is the 0 in this room, if I say this is the 0 in this room, and I say this ball has a potential energy of negative 2, what does that mean? Below 0. Okay. Which way is it going to head related to the 0? What's that?
I didn't see where you
I'm sorry, 0 I said was right here. So negative 3 joules means the ball is where? somewhere below that. Okay? Now, do you expect the ball to head towards 0? No, you still expect the ball to do what? Go more and more negative. So what that tells me, and remind me, where is 0?
Where we said
It would be at infinity. So what I'm saying is it more likely for this charge setup to head out towards infinity, or to kind of go more towards themselves? Well, the negative on this says these are not going to head towards infinity, right? That if anything, it's below that spot. Now, why does that make perfect sense? Well, that makes perfect sense because what is your biggest charge? Negative 200. And what does the negative 200 do to the other two positive charges? Pulls them inward. So would you expect this setup to expand or to come closer together? You'd expect it to come closer together, right? So I could ask you this. I could say, hey, what's the change in potential energy to take Q1 from its current state out to infinity? In which case, this is the potential energy I said from here to infinity. So this would be potential energy initial. And what would potential energy final be if I had that thing out towards infinity? Well, technically speaking, you could recalculate. You could just recalculate this. But as these numbers get gigantic, right? This is the limit conversation from yesterday. What do both of them head towards? Very quickly they head towards 0. So the argument of R is infinity is it's so far away that each of these is 0, which means the potential energy final is, why do you keep doing this? I don't understand. I'm pressing something. This is 0. So I would get minus negative 2.7 millijoules. So the change in potential energy is 2.7 millijoules. Is that naturally going to happen? Is change in potential energy naturally going to be positive? No, it's not. The only way this would happen is if something was pushing it the other way. Now watch this. What if, instead of saying one of the spots is at infinity, what if instead I said, well, let's compare this orientation to a separate orientation in which I move this guy right here. Okay? So now the charge is over here. Which of these two scenarios is more likely? Well, given the fact that just conceptually, before we ever do numbers, which one's more like, is it more likely for it to be pulled in or pushed away? Well, what's doing the pulling? Negative 200. What's doing the pushing? Positive 67. Right? So, which situation is more likely? This one, the initial, or the final position? Now, if you didn't catch that, mathematically, you could very easily figure this exact same thing out, because actually you'll notice I did this in such a way that none of this changes except for this is now divided by 3 centimeters, halfway in between the two, and this is now divided by 3 centimeters. So what happened to both of these two numbers? They both got bigger. So ultimately, that would mean, we don't need to do the calculations here, potential energy final is just double what the initial was, right? So negative 5.4 millijoules. And which position did we say is more likely? Final is more likely, yes? And mathematically, how can you clearly see from the mathematics that it's definitely more likely?
Where it has the largest consumption.
It's more negative. Okay? So you remember when they talked about water, water has a particular angle to it. You remember this, yes? Okay? Do you remember that water has a particular angle? Do you know what I'm talking about? Okay, there's oxygen, there's hydrogen, and you hear the whole conversation back in chemistry of water is polar, and that's because oxygen holds on more than the hydrogen, and specifically because it is bent in this particular way. Now, how on earth did they figure out exactly what that was? Well, hydrogen basically has a charge of, roughly speaking, it's not perfect, but basically positive E. And that's roughly negative 2E, roughly speaking. It's not perfect. So what they then did to figure this out is they used a computer program and figured out where is the most likely position for them to be, or what was specifically said all the time in chemistry, its lowest energy position. Its lowest energy state is simply, what's the lowest energy state of the ball in this room? And in general, without doing fancy math, any normal human being can tell us the ball is most likely to go to the room, right? Okay, why is that? Because there is a force down. So where do we expect the most likely place to be? Down. We are basically just mathematically reversing this particular process and looking at all the possible orientations and going, hey, the one with the lowest number is the most likely position for all of these things to be in. Yes? So I'm going to move these H's around. Why can't I just infinitely take these H's and make them closer and closer and closer to the oxygen? Because as they get closer to each other, what does that do to the push? Pushes it more away. So there is a fine line between pulling them in, pulling them in, pulling them in, making these two more and more negative, and making this guy more and more positive. So there is a lowest number or lowest energy state, and it is one in which I believe that ends up as 100 and I think it's 105. I can't remember specifically. Do you guys remember what the angle was between oxygen? Yeah, it's no big deal. Okay, it's not that important, this process, but that's how they figured this out, is they literally found the lowest energy state. So I told you when I started this problem over here, there's two ways of doing these problems. And the first one is, one, look at a single charge. How do you get Q1? So you'd look at this one and this one. The second setup that you're going to get a lot on your homework is, what is the energy of this entire orientation? In which case, you add up every single possible pair. 1, 2, 3. So if I had a setup with this many charges, and I asked for the total energy of, say, this one, how many pairs would you do? 3. Yeah, you'd do 3. But if I asked for the potential energy of the entire orientation, discuss quickly in your group, how many would you do? Discuss quickly in your group. Is it just that easy, or we're not understanding the question? The question is, how many different pairs? If I call this, I'll call this Q1, Q2, Q3, and Q4. I said if you're just looking at the energy of one, it would be 1, 2, 3. Okay? What is it if you want the entire energy of the entire orientation? You have to do every single possible pair. How many are there? Everybody got it? No, not 12. 6. 1, 2, 3, 4, 5, 6. Fair enough. Okay, what about this? What if I had 1, 2, 3, 4, 5? If I wanted to find the energy of this guy, how many would there be? 4, that's easy. Okay, more than likely you're not going to get that high on the problems. But if I wanted to find the entire orientation, discuss. I think it's 10, yes. And I'm apologies for going to accidentally make a pentagram. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You guys saw last year how often I accidentally drew swastikas, right?
Oh, yeah.
Because of circular motion, it would be like, hey, an object's going around the circle. Here's velocity, here's velocity, here's velocity, here's velocity. What's direction acceleration? It's towards the center, Spainhour. Yeah, that's not a great idea. All right. So I would regularly, I don't know if anybody noticed this, when looking at stuff circular motion last year, I'd regularly go here, here, and then I would stop, like right there, and just go in that direction. We're just going to stop right now. All right, moving on. So there's energy. Now, what is the value of this? It mathematically allows us to simply calculate with scalar numbers which position is more likely. right? Simply put, if I told you, hey, there's two orientation of charges. One is at 50 millijoules. You should already be able to tell me, is that charge set up expanding or coming closer together?
Wait, what?
Is that charge set up expanding or coming closer together? Just if I tell you that its total is 50 millijoules. It's expanding. How do you know that?
Because we're positive.
Where's 0?
Below it.
0 is below it, so 0's out at infinity. It would be expanding. Let me give you a for instance. Here's a for instance of that. All positives, right? Actually, quite frankly, I could also do all negatives. What are all of the energies of these going to be? All going to be positive, right? And then I could kind of expand them and go, which is more likely, here or here? Absolutely. And mathematically that works because since the distance goes up, what happens to the energy? And what happens to this orientation as all these charges head out towards infinity? All the energies head towards 0. But if I enter a positive into this particular mix, well, now I've got repulsion over here, but both of these are causing attraction. So now it matters what the size is. What if I had this? What if I had this set up, okay, and all of these are the exact same size? What if I say this is like positive 60 microcoulombs, that's negative 60 microcoulombs, and that's positive 60 microcoulombs, okay? And we look at the energy on this guy right here. Well, what's going to end up happening is that these values, assuming these distances, once again, equilateral triangle, are the same, the total energy here is actually 0. What does that mean? It means that the difference between energy in this state and out at infinity is 0. Why does that make sense? Well, if I start moving this guy this way, kind of along this line, we don't worry too much about direction. What is that guy going to do to it as far as force is concerned? Push it. What's that going to do to it?
Pull it.
Pull it. And how much are those going to compare? Those are going to be equal. And so what's the net force on this guy? 0. And if the net force is 0, how much work is being done to it? 0. And would it naturally then head out towards infinity and not change its energy in any particular way then? Yeah, it's exactly like that would be like if nothing was there at all and this is just going through space. Here it is with the particular velocity. Would you say any work is being done on it in space? No, because there's not any force acting on it. It's not speeding up, slowing down. Questions, concerns here?
What about the negative? The negative would have.
The negative would pull it. I'm assuming, I'm just looking at one right now,
Oh.
right? The negative would pull it in equal amount as the positive would push it, and therefore this thing is just going to continue going on out forever. Okay, so basically if I've got a setup of charges, and I say, hey, here's a positive charge, here's a positive Q, here's a negative Q, and another positive Q. And I look at this guy right here, and I tell you that this guy right here is negative 10 millijoules. And this spot, I calculated, don't worry about it, I already calculated it for you, is negative 50 millijoules. Which spot is more likely? Negative 50 millijoules. And if it moves between these two locations, what's the change in potential energy? Negative 40. This final is negative 50 millijoules minus the negative 10 millijoules, or negative 40 millijoules. Does that naturally happen? Yes. How much work was expended during that time? Positive 40 millijoules. What's all that work probably going to become? What energy will that work become? Not thermal. Kinetic. It's now moving with 50 millijoules now prior that it didn't have before. Yes?
Okay, so because you said if there's two forces that are acting on this that are like the same, but they're the same but opposite, same magnitude opposite, there's going to be like nothing's acting on it at all.
Yep.
But if it doesn't have a velocity already, and you just have you arbitrarily have like two positive, one negative somewhere, and they all have the same magnitude, they're going to form an equilateral triangle. That's why
Not
the
necessarily.
triangle is equilateral.
Like you saw earlier with the water element. There's two negative. There's two positives and one negative there. They don't automatically form an equilateral triangle.
Yeah,
It depends on how strong the charges are.
but shouldn't they, if the charges are the same magnitude, but like the minus is obviously negative, but the two positives are the same.
Well, I don't know. And honestly, that's the whole purpose of this. The whole purpose of this is kind of going like, hey guys, you know how we focused a ton on vector stuff and which way it's pushing? Who cares? Okay? Here's what we're doing with energy. We're basically using a mathematical trick to go, what's the energy here? What's the energy here? Oh crap, which one's bigger? Well, this one's bigger, so this one's more likely. And they're going to head that direction. Okay? What we're trying to get to is a spot where we can mess around entirely with energy and we don't have to give a crap where they go. Because I got bad news. I don't know if you've noticed this. It's hard to look at these charges. It's hard to spot where they're going to go. So it would be really nice if, let's say, for instance, open that quickly. I don't know if I could, if I could look at a device and look at two spots on that device and go, you know what, this spot right here is less likely to be, more likely to be, and this spot here is more, this one's more likely, this one's less likely. And the separation between the two of them is about 1.5 joules. Now, I don't really care where they go. If one goes from this spot to that spot, how much energy was just spent? 1.5 joules. So I don't have to care where they're going to go, how they're going to go. I know how much energy they're going to use. In terms of gravity, it would be like, imagine that we don't just have one ball. Imagine that we're at a ball pit, and there's thousands upon thousands of balls that you're potentially dealing with, and someone tosses them all up in the air, and you're like, what's the energy? Like, this is a lot of math. I don't have to. Someone goes, you know what? This spot where they started on, this spot is, let's call it 2, and the ground is 0. So how much energy did each ball particularly put out? Well, I don't care where they went in total. This one started at 2, went at 0, it decreased by 2, so each one had 2 joules come out. Do I have to give a crap where all of them went in the interim? No. Meaning, if I look at this location and it's -10, and I look at that location and it's -50, and I know they're starting here and ending there, I know a charge will definitely put out -40 millijoules. Now this will lead me into today's conversation, but here's the problem. Is it going to be easy to figure out how much charge is there? No. Am I going to need to know how much charge is there in order to get how much energy there is between that spot? Yeah, it's kind of like my example with the balls. Well, to calculate the energy of a ball, what equation would you use? That 2 and that 0 I commented.
MG.
You need to use MGH, which means you need to know M, right? Well, in this particular case, both equations for potential energy, both the uniform one and the non-uniform one, kind of need to know how much charge is in the case, but it's not easy for me to figure out how much charge is going to be there. So let's do something that we did very similarly with electric field. Do you need to know how much charge is going to go in this field in order to calculate electric field? Do you need to know how much charge is here to calculate electric field? No, what's the equation? What's the equation for electric field? Its definition. The ratio between force and charge, right? It's how many newtons, what are the units on that? Newtons per coulomb. It's how many newtons would be on 1 coulomb. And then, of course, it's nice if we do plug the coulombs in, we can rearrange this and we get our mg. Yes? Now, what if I want to do the same thing with energy? See, to get energy, it's basically the exact same setup, except we need to know some height, right? So in other words, this 1 meter above the ground, we just talk about gravity first, okay? If I knew the mass, I could calculate its potential energy with MGH. But what if I didn't know how much mass was going to go there? Well, I can make a ratio. How much energy would be on a certain amount of mass? Okay, and it would be calculated by g times height. What is g? Why is it b? How much is it? 9.8. Okay, and let's look at 1 meter right here. At 1 meter, what would that number be? 9.8. What would its units be?
That's meters per second squared.
No, let's look over here. Sorry, you look this side. You're right, but what you be? What's this? Joules per kilogram. Just like this was newtons per kilogram a second ago. So why would it be nice to know joules per kilogram? What don't you have to know? You don't have to know the mass. And this is, you're going to hear me use this analogy a stupid amount of times. I apologize. But imagine you go to the park with like a toddler. Okay? This is like an empty hill. Okay? If I had 2 hills, okay, when I go to the park, let's say I'm taking my 3-year-old son. You laugh because very, very quickly, without any child being on that hill, every single one of you, there is a massless hill right now. Every single one of you can deduce very quickly one of them is slightly more dangerous. Why? I bet you would. I'm not going to sacrifice my child. Why? What are you looking at very quickly to do that? You're looking at the height. AKA, you know the gravitational field is the same everywhere on Earth, so the only thing you have to look at in this case is how much height there is in that particular case. You know that this hill will have a lot of energy for a certain amount of mass. Yes? You don't need a mass on that hill in order to tell you this. Also, if you wanted to know how much energy, you could simply once again rearrange that equation, and that would just be the GH that you had a second ago times M, aka GH is the potential energy for a certain amount of mass. So all you got to do, I've got 1 meter right here. You said it's 9.8 joules per kilogram. So what's the only thing you need to know if I put an object right here to know how much energy it's going to have? Multiply by kilograms. 1 kilogram right here would be 9.8 joules. 2 kilograms would be 19.6. You get the idea, yes? So now, here's what we do. Potential energy is equal to negative QED. And it's also equal to KQQ over R. Except knowing how much charge is going to be in a particular area is not a very easy thing to do. So we're going to make a ratio of potential energy to charge, specifically the test charge, not the source charge. And that's going to create 2 equations. This guy over here is going to end up as what? What's that? Negative ED. And this guy right here is going to end up as? K, Q of source, over R. You'll notice that this equation right up here is extraordinarily similar to the GH that I did just a second ago. Now, what would the units on this guy be? You'll notice I've not given it a variable yet. What's that? This would be joules per coulomb. And you know what? I don't like joules per coulomb, so let's find a fancy particular individual and give him a name. Let's go ahead and call this 1 volt. This is known as, it's actually not voltage, I'll get specific to that in just a second. This ratio right here is known as potential difference. Sorry, it's actually, no, it's not, I apologize, it's not potential difference. It's electric potential. Now there's going to be a lot of information that we're going to go through, and I'll practice these a lot more tomorrow as we also talk about capacitance tomorrow. And I'll try to wrap up quickly so that you can do a little bit of work with these. But I do want to do some charts to kind of separate out all of the ideas that we've discussed kind of so far to kind of talking about that, and also show you where actually voltage that we regularly see actually occurs. Okay, so for starters, let's begin with this. This guy is known as electric potential energy. Now, as we stated before, is electric potential energy by itself dangerous? No, it's absolutely not. This is the on top of the hill situation or on top of the mountain situation. This is known as electric potential energy difference. Now I'm giving you vocab as we talk about this, but ultimately this is guess how these two are related. This is just a change in that. These are the initials, these are the finals, this is how much it's changed. You can see me have that kind of conversation all the way back here towards the beginning of today when I was doing this guy right here. Each of these, -10 and -50, those are representations of electric potential energy. The difference between the two of them, that's the -40 in that particular case. And that's energy actually being used. Because if I had said this is -10 and that's -10, then the potential difference is 0, in which case there's absolutely no energy whatsoever. Now, coming back over here, this is known as electric potential. So you could probably deduce this. Let me finish this slide and then I'll get you. Okay? You could probably deduce the name of this one with a little bit of recognizing patterns. What's this guy called? Electric potential difference. Now, the first thing that I will point out is that since there is the word electric in every single one of these, when we are talking about electricity, we usually drop the word electric, meaning this guy's potential energy, that's potential energy difference. This is potential, and this is potential difference. And potential difference is used so often by colloquial people in all of the United States that that's such a stupid fancy name that they basically went, well, how do we measure potential difference? We measure with volts. So let's give potential difference a different name. This guy is known as voltage. So if you ever hear that a voltage is a particular number, that's what it's talking about, the electric potential difference. So a standard battery in the United States, and by standard battery I mean one of the lettered ones, C, D, AA, and AAA, all have the exact same potential difference. They are 1.5 volts. What does that mean? Well, it means that the difference between these two spots is 1.5 volts. And what did I say a volt was? Joules per coulomb. And I kind of already did this a second ago, but I'll do it again. What does that mean? Well, it means one of the two of these is more likely. And if 1 coulomb goes through this system, if 1 coulomb goes through, how much energy is going to be used? Correct. 1.5 joules. In other words, you know how the nice thing about electric field is that force electric is equal to Q times E, right? So once you have electric field, you can just multiply by Q. The nice thing about potential difference is Q times potential difference is its potential energy. But do I know how much charge is going to go through this battery? No. I could hook this up to a calculator, in which case the calculator doesn't pull very much charge at all. Okay? Doesn't pull very much charge at all, doesn't need very much energy at all. I could hook this up to a piece of electronics like this, in which case the current is much, much higher. In which case I can get the energy out of it. It's going to use a lot more charge in that case. Here's a better example. Oh shoot, Rafelli has it right now. Well, fine, I'll use the Van de Graaff generator in the back. The Van de Graaff generator, you know the Wimhurst machine, what it looks like, or the Van de Graaff generator, have produced voltages that I told you were crazy high numbers. If you remember, the Wimhurst machine, I told you produces somewhere on the order of 40,000 volts. And yet I am completely fine with you getting shocked by it. If you get hit by 40,000 joules, are you okay?
No.
No, that's a small piece of TNT. Okay, 40,000 joules. Okay, relatively small. All right. Now, why are you not going to get 40,000 joules if the Wimhurst machine hits you with 40,000 volts? The amount of charge that is going through the air is going to be very, 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 very small. On the order of usually micro. So if this is times 10 to the negative 6th, and that's times 10 to the 5th, I'm sorry, I said 40,000, so times 10 to the 4th, the total is actually on the order of times 10 to the negative 2nd. Is that big of a deal? People get hit by lightning. Now, it's not great for them. Right? It's not ideal. But they do. They survive. How can they survive? Because there's not that much charge passing through the voltage. Voltage is basically this in a nutshell. I kind of did this a second ago with a charge. Oh my, there we are. I said, hey, this spot right here is negative 10 millijoules, except you'd have to know what charge is here, yes? So now all we're saying is that there'd be negative 10 millijoules if there was a Coulomb there. Or this is the same thing as negative 10 millivolts. And this spot right over here, who knows, but let's go, that's negative 50 millijoules if there was 1 Coulomb. So this is negative 50 millivolts. And it's just like a hill, an empty hill. Do I need to put a kid on that hill to know that it's dangerous? No, I don't have to put a kid on that hill. We could just say that I know that if a kid went up there, or a child went up there and went to the bottom, that it would have something like 200 joules per child. Now, does there actually have to be a child on that hill to make that measurement? No. Now, if a child does roll down that hill, then energy is going to be spent out in a bunch of different forms. Like in this particular case right here, I can convert this electrical energy into sound or light, aka your calculator. The wall outlet right over there is 120 volts. Is that potential difference or potential? Is that potential difference or potential? No. It's difference. What about the outlet? Tells you that it's potential difference and not just potential. Close. There's two sides of it. So one side is more likely than the other. Guess how much more likely? About 120 joules per Coulomb. That's what voltage means. If I go here, okay, and I have an electric field of 10 newtons per coulomb, and the separation between these sides is 1 meter. Potential is equal to negative ED, where the distance is measured from where? So let's say it goes from here is 0, and here is 1 meter. Potential difference would be VF minus VI, or negative DEF DI. And once again, we're going to factor out the E. So the change in voltage is equal to negative E delta D. AKA, this would be negative 10 would be the potential difference between the two. What would the units on that be? Joules per Coulomb, or yes, negative 10 volts. So I gave you a situation where that outlet right over there is potential difference because there's two sides. The lines of power that run to like practically every building are more than likely at 20,000 volts. And yet you see birds land on them all the time. They're completely fine, right? If you don't know this already, they're completely exposed up there. Those wires are not insulated in any particular way. They're 100% exposed. And yet birds land on them, they don't get fried all the time. Is that 20,000 volts potential or potential difference? Potential, because it's just one location. So why is it that birds are completely fine? Well, they're touching two spots, right? Well, what's the potential in that foot? 20,000. What's the potential in this foot? 20,000. So what's the potential difference between both of their feet? 0. AKA, this is like you walking on top of a mountain. Do you have a lot of potential energy on top of a mountain? Yeah. Are you completely fine walking on top of a mountain? As long as you stay at the same potential energy, so that the potential energy difference is 0, you're completely fine. When I say potential is 20,000, what that means is that would push a lot on positive charges or pull a lot on negatives. So, is that wire pushing or pulling on the negatives inside the bird's body? Yes. But this wire over here that's touching this leg, what's it doing? The exact same opposite way. So is there any net energy on their body? Is there a net force on the charge in their body? No. So there's no current passing through their body. Now, when would it be dangerous? Let's say I was operating on top of a particular line. What would be very dangerous for me to do? Now, metal boots would be fine. Yeah, if one of those power lines fell to the ground, why is it now a lot more dangerous? Guess what the potential of the ground is, a neutral source. It's neutral. Why is an object neutral? It's an equal amount of positive and negative, and therefore the potential of the ground is 0. So if I hold on to that power line of 20,000 volts and touch the ground, is that an issue?
Yes.
Yes. This is pushing a lot more, and there's going to be a current, there's a potential difference between my hands now of 20,000 volts. So yeah, that's going to be a little bit more of an issue. This is the difference of, yeah, the bird on the line is like walking along the mountain. Me touching the wire and touching the ground is like me falling off the mountain. Yes, if there's a potential difference, it's going to cause an issue.
So if I stuck both my fingers in the outlet, I would be fine.
No.
I'm
Okay, no. There's an important difference. This is an excellent question. Also, don't do that. Okay. There's an important distinction between the two of these.
Oh,
Okay?
my feet, I guess, are touching the ground.
No. That's not why. That's not why.
No?
Let's make sure we address this. Okay. The power line outside. The power line outside is one potential. Basically, it's kind of like the top of a hill, the top of a mountain out there on the power line. If I was saying hanging from that power line, I would be completely fine because the potential here is 20,000, the potential here is 20,000, and therefore the potential difference is 0. But as I've stated already, the power in those outlets is 120 volts. Now, is that potential or potential difference? Difference.
Okay, but how do you know?
Both sides.
Wait, like I'm confused by what you mean by both sides. What are both sides? Like the front and back, or I'm confused?
Okay, no, this is fair. This is fair. All right. If you had to guess, no, you're fine. Stop. You're fine.
Okay.
Let me share. Okay, so this battery I said has a potential difference of 1.5 volts or 1.5 joules per coulomb. Yes. I don't know what the potential of either sides of these are. I don't care. Okay. The difference between those is 1.5. So if I touch both sides, is there technically a flow of current between me right now?
Yeah.
Yes, I'm not worried about it because it's 1.5. If I touch both fingers the same location, is there going to be any current between it now? No, because the potential difference is 0.
Oh.
Okay, so outlets, the easy way to tell this is you're only going to get electricity flow when there's a potential difference. You can kind of think about the flow of electricity kind of like water, and as I've mentioned a couple times, potential difference is like an empty hill. If potential difference is an empty hill, potential is like the spots on that hill. Here's the potential, here's the potential, right? Which spot is more likely if we were talking about gravity? Absolutely. And so if I put an object here, what's an object going to do? It's going to roll through the potential difference, right? And that potential difference is, let's make up a number here, 200 joules per kilogram. I'm trading back and forth between kilogram and coulomb right here. So if I had 1 kilogram, I would get 200 joules going through that particular spot. But do I actually have to have a mass here to figure out what that potential difference is? Just like I don't need a child on an empty hill, right? So again, if you're looking at a hill, before you said which one of these two hills would be more dangerous for my kid?
The left,
Obviously the left. And why did you say that?
because you have higher potential.
Because it's higher, right? It's what you said. So if these were potentials, which one has more of a potential difference? This one over here has a larger difference between those two values. Now, here's a major difference between electricity. Sorry, Jaden, I see you, but I want to address this before we go. Positives go the opposite way of negatives. Yes? And we don't give a crap because we don't know. Meaning, if this was a potential curve, okay, potential related to just some distance in the x, so it's moving along the x, okay, what we would expect a positive to do is go this way. We'd expect a positive to lower its potential, right? What would we expect a negative to do? Go the opposite way. Kind of like I said the other day, it's kind of like flipping this around. If this is a hill, where do you expect a ball to most naturally be? Bottom. This would be like a positive. It'd be the lowest potential. But what do you expect a negative to be? You expect a negative to be right up here. Quite frankly, we don't give a crap. Why? Because if that's 1.5, or let's make the numbers easier. If that's 10 and that's 0, the potential difference between that spot is 10 volts or 10 joules per coulomb. So if 1 coulomb goes through, I get 10 joules. What happens if a negative 1 coulomb goes that way? We also get 10 joules. Either way, we get 10 joules of energy out. Do we care whether it's positive or negative? No, not really. This is 1.5 joules per coulomb going through this system. I don't care if it goes right to left or left to right. All I care about is that it powers my calculator or powers my computer. I don't care whether or not it goes left or right. I care how much energy comes out of this thing. All right, JD, you have a question, concern?
So for like the outlet, is the voltage like the difference coming from like the left and right, like
Yes.
sides of the hole?
Yes, there's the hot wire, standard way of hooking these up. The hot wire is actually usually 120. Weirdly, in setups, typically the neutral wire and the ground wire both run at 0 potential. So they actually equally have the same potential between the two of them. So if you attempted to connect a setup, you did it poorly, and you hooked up both sides of the outlet, one to the neutral and one to the ground, there'd be no flow of electricity whatsoever because there's no potential difference between the two of them. If you hooked it up incorrectly, you could also hook it up so that the hot wire is connected to the ground. That would get you a difference of a 120, but it would be negatively set up in terms of safety. We'll talk about that a little bit later on. So the ideal way to set it up is that you have the hot wire at 120, you have the neutral wire sitting at 0, okay? And so you have a potential difference of 120. The ground wire is then there, and as we've stated before, the ground wire has a potential also of 0 because the ground wire is connected to the ground, and the ground is very, very neutral because it has an equal number of positives and negatives. And if it has an equal number of positives and negatives, if positives are pushing that way, equally the negatives are going to pull this way, which means the net force on any charge is 0. It's 0. There is no net force on it, and therefore there cannot be potential energy, and therefore there cannot be potential on that particular guy right there. Questions, concerns? The math is extraordinary. I didn't worry too much about the math today because it's extraordinarily similar. The only major difference, honestly, in the math of potential versus potential energy is this. Here is your problem for potential energy. Boom. And you can use negative QED. Watch what happens if I get rid of that guy and I just look at its area. Potential is negative ED. How do you get the change in potential energy? You take UF minus UI. How do you get the change in potential difference? VF minus VI. Okay? In the non-uniform ones, I'll finish with that actually over the last 5 minutes. In the non-uniform situations, earlier we were doing this. We were doing positive, negative, and a negative up here. Now, we just get rid of that negative up there, and we look at its area. And we can calculate the potential with KQ over R. If I want the potential of that spot, I would find the KQR of the positive and the negative, and guess what I would do with the two of them? Add them, because it's scalar. And what is the potential out at infinity? 0. It's absolutely 0. So I could compare that spot and that spot right there. Of course, the distance is changing, and then the difference between the two of them would be the potential difference. All right, let's give you this chart here real quick. This even goes back to stuff from last chapter. There's 4 things that we kind of want to connect all together. Force, electric field, potential energy, and potential. And for each of them, I will give you definition. What does it look like in a uniform electric field? And what does it look like in a variable electric field? There is no definition for force. It is what it is. How do we calculate force in a uniform electric field? I say QE, but yeah. And how do you calculate force in a variable electric field? Coulomb's law, KQQ over R squared. And I'll even put Q of source and Q of test, even though they're kind of arbitrarily chosen. The definition for electric field is the ratio of force to charge. So what you'll notice about all of my guys right here is I'm just going to take each equation and use this. Force divided by Q would basically just be E. So I'm not going to write that there. That is just the electric field if it's uniform. How do we calculate variable electric field? Q of source over R squared. Key things to remember about these two. These are both vectors. So you have to do vector addition. What's the definition of U? Energy is all defined as, what's the main concept all of energy? Work. Force times displacement. So, force, oops, my apologies. This is just potential, so this should just be qued. Qued. Okay, and then how do you get the variable? Okay, Q of source, Q of test over just 1R. What is the definition of electric potential? Let me finish this chart and then answer your question. What did I say the definition? So the definition up here of electric field is the ratio from force to charge. The definition here is the ratio of energy to charge. So, as before, I'm just going to take these guys and divide by Q. So we have qued, negative qued. Now we have negative ed. I was asked a preview years ago if there is an eddy. I said yes, 100%. There's eddy currents. So we do have qued, ed, and eddy. If you don't get that reference, I'm sad for you. All right, and what's the equation in a variable field? That would be K, Q of source over R. And as I just did it a minute ago, both of these two are scalar. Now, a quick point of interest on this chart. Please notice very carefully that I do not have delta U on here or delta V on here, but the way that you calculate any deltas, the way you calculate the change in anything, going all the way back to physics 1 is final minus initial, correct.
Wait, what's eddy?
Eddy currents, it's not on this chart. Eddy currents have to do with electricity that we'll get to in the next coming chapters. Sort of, actually, we'll get both.
Sam, you should do, oh my gosh, have you been to Six Flags? Have you seen the new ride?
I don't go to Six Flags except with you guys. That's
Yeah.
the only
Okay,
reason
well,
I go to
anyways,
Six Flags.
Have you seen the new ride?
No, I haven't been to Six Flags except with you guys.
Okay, so the new ride, you've got to look it up.